So a lot of absent this morning. This is a good time to call attendance, right?
It's the best. Perfect.
But first we need to finish our schedule. So pretty much is the right schedule. So we are not behind the schedule. So let me first finish this chapter. So in this chapter we are talking about how to use the memory. Okay, so the main purpose of using memory is to load our instruction code that can be used by the CPU eventually to bridge the gap, speed gap between the permanent storage and the CPU. So the main problem of using the memory is considering the price. Comparing price with secondary storage is expensive and relatively small, and also it's a volatile storage, which means that we cannot use the memory, the permanent purpose. So nowadays we have the DRAM or the memory that can keep the that can be persistent storage. But most of the main memory that used for our computer system is still volatile, so we need to manage we cannot use the memory as a persistent storage, but we need to take care of such a thing. So eventually the problem is how to allocate the memory space for process. So first approach is a contiguous allocation. Before that we talk about the hardware support, how to protect the process, because due to the characteristic of the memory itself is nothing but a sequence of address like the number of seat here. So we don't know if you, even though you reserve the seat, the first row, but who cares? You sit on the other rows. But the operating system needs to take care of such the space to protect the process. So for the protection, we are using basically base and the limit. So this approach used a lot in any management issues in the memory. So, but name is slightly different, but same idea. So where is the starting and where is the end? To decide the end is what is the size of the memory. So using that, the ideas of CPU can implement the hardware, part inside the CPU to protect each process. So then finally we can allocate the memory space for each process. The first approach is a contiguous allocation. So in other words, it's a partition. So for that multiple partition allocation, so we can think about the different approaches, like the first fit, best fit, the worst fit. We cannot say the one is the dominant than other. Depending on the situation, we can select the one of this approach. But nowadays, we don't use a lot this kind of approach. It's a simple, but it's not very practical due to the problem of the fragmentation. So there are two types of the fragmentation. The one is the external fragmentation, which you can imagine. So you encounter such an external fragmentation problem on the disk management. So if you used before the Windows, old version of the Windows, so you probably did the defragmentation, like the compact process, to change the location of the file, then you can speed up. So that is the external fragmentation. Means even though you have the even though your total amount of free space is big enough to allocate the process, but if they are separated, segmented, you cannot allocate the process to that free space. So that is external fragmentation. Solution, you can do the compact process, which means swap out all the process and free up, make the big chunk and upload. But practically it's not the possible. It's not the practical because it takes a long time. there's another type of the fragmentation, which is internal fragmentation. We will see a little bit more internal fragmentation. Internal fragmentation means it allocates the memory space, but not each processor cannot keep all the space, each byte, each bit. So there are something remainder of the space inside the chunk of the memory. So this is called the internal fragmentation. So it's not it's not serious than the external fragmentation, but still it reduces the usage of the utilization of the fragmentation. Also, some of the data structure intentionally create the internal fragmentation. For example, database use the database block, but it is recommended to use only 50 to 60% of each block, and the other 40 to 50% should be free space. So this is an internal fragmentation. You cannot use this part, but intentionally you can create such an internal fragmentation. This is called the free space in a block. So according to the Oracle term, it's called the PCT free, percentile of the free. So you can specify actually how much is free. The reason, but why we made the intentionally free space. For future use, for example, if I update first, I put the lead as the name, but we realized that we missed the first name. So if this is, for example, the fixed variable length, so there's no more space after this. So you need to, if you use all the block of the storage, you need to use another block, then the length. So there is the first name, like this one, which means you need to read 1, 2 IO. So they ask actually this is called the chain, the block. So sometimes it can be multiple chains, 3, 4. So to read the one data, you need to actually do the several multiple IOs. This is the overhead. To address this problem, we can, whenever update or the change of the data inside the block, we can use this free space future. Then this one, you don't need the extra IO, so you can still keep the same IO, then modify the data. So sometimes we can use such intentionally create the internal fragmentation for future use. So one of the approaches to address the problem of such a contiguous allocation is we make some group of meaningful chunk of the data. Instead of the entire chunk, we can, this is the process, but the one process consists of the several meaningful chunk of the data structure, such as the subroutine stack, the or the other. So because mostly when in your program, first time you can call only the main program, not all of this instruction. And from the main program, you can call the subroutine. So what we need is, what CPU need is only the chunk of the instruction. By considering this idea, if we can create such a chunk of the meaningful chunk of the process, then allocate the memory. Not entire the process, but such a meaningful chunk of. That is called the segment. So segment is one of the ways to address the problem of the contiguous allocation. So instead of the entire chunk of the process, so we can allocate the segment by segment. Same problem as the contiguous allocation, we need to protect each segment using what? Mapping table. Okay? So we can consider the segment table, which is the same as the mapping table that we discussed the last one. Where is it? It's also in the memory. So which means in your register, you need to know where is the starting of this segment table and the length of this segment table. That is the register name, segment table base register, segment table length register. So it's a base and limit. So basically same idea as the base and limit register that we have seen the contiguous allocation. So as we have seen before, the basic architecture of the CPU. CPU has several different types of register. One of them is such allocation, relocation the register. Relocation register is not just one, so they actually design the several possible relocation register. One is used for the segment, another one is used for the contiguous, the other third one. So there are actually the several such a register that you can use in your operating system. Okay, so this is the schematic view of using the segmentation hardware. This is actually hardware implementation. Then it's the same as base and limit. Okay, it's not the operating system implementation, but it's the CPU vendor. Actually, if they decide to use a segmentation-based allocation, they need to create the design and make the circuit design for this one. So this is actually hardware implementation to protect each segmentation. Idea is the same as the base and limit, the hardware. So instead of the memory, the mapping table, so we have the segment table. Segment table has basically segment number and it has the limit and base. So base is the starting address and the limit is the length. So we can calculate, we can check whether the program counter. So CPU actually would like to access the instruction that is specify the program counter and the location. So check which segment is used, then get the base and limit. Using the base and limit, the process check whether that is the valid address or not. If valid means between the base and base plus limit. Then you can access the instruction. Otherwise, we call the interrupt. The thread. So that is the segmentation hardware. Okay. So this is an example of how to use the segment. Instead of the process, one process has a number of the segment, and it has the base. For example, the main program. So first, the module of the program that can be executed is the main program. So main program is a segment 2. So first check the segment table. How do you know that? It's in the memory. So you have the segmentation base register. So first check that register. So that is probably somewhere in the memory, or sometimes it can be cache. So it has the location of that. Then check the segmentation number 0, 1, 2. The 2 base is 4,300, and the limit is the size, length is 400. So then check the pass through the testing. So if that is okay, then that will be the 4,300 here and 400. This is okay. So you can access the specific instruction specified by the program counter finally. So this is the segmentation based. So this is so far the chunk of the program will be allocated to the memory. So still you need some various lengths of the chunk. Usually the big chunk of the memory. Still the segmentation based allocation need the cause the fragmentation. Even though you have the free space, but if your segment the size of the segment is bigger than the biggest chunk, you cannot allocate. You need to compactation, or you need to swap out some of the processes. So nowadays we do not use such the segmentation based or the contiguous allocation due to such fragmentation issues. So nowadays we are using different approach that is called the paging. So paging means this is our program. Okay, the program is eventually this program will be loaded into the memory. This is the memory. This is our program. Okay, so contiguous allocation, we try to find enough space, entire chunk for the program and the memory. The segmentation base, we divide the program by the segment, meaningful chunk, meaningful the set of instruction, then the segment by segment allocate. Still, it calls the fragmentation. So instead, why don't we? Because idea is like that. When we first execute the program, when we run the program, not entire code, not entire instruction are executing at the same time. Even some of them are not needed. So first we need the first instruction of the main program. Then the process sequence of that thread of the instruction, then call the subroutine. Then we don't need the other. So why don't we call the bring the such an instruction whenever we need? At that time, we don't have to load the entire chunk of the instruction. Instead, there's some small part of instruction. So to implement that idea, we are going to divide the program, our program, by fixed length of the unit. Okay. So let's say this is a 512 byte. Okay, and the 512 byte, and so on. Okay, divide by the same size of the unit, and also we divide the memory by the same size, the 512 byte, 512 byte, 512 byte. Then we allocate this unit by the unit whenever we need. Okay. It's a similar idea as a segmentation base, but the segment is, we don't know the size of the segment. It depends on the meaningful chunk. So it depends on if the module is the big and the segment will be big, and sometimes small, sometimes small. So we cannot guarantee it's allocated to even though you have the free space. Instead, we firstly divide by the number of divide by the fixed size of the unit. Then also divide the physical memory by the same unit. Then allocate this unit by the unit. This is always a 512 byte, type 512 byte, and so on. This is also 512 byte, 512 byte. Okay. Then allocate this one. So at this time, the fixed size of the unit is called the page. So this is called the paging approach. So first one is contiguous allocation, and second is segmentation-based allocation. But practically nowadays we use the page by page allocation. At this time, this physical memory is called the page frame. So we have a number of page frames. And also, this program, this is our program, like the A.out or the MS Word.exe. So this is our program. Our program is called the logical, the memory. Okay? So our goal to implement the paging is, our goal is allocate the pages, number of pages of the logical memory to the page frame in physical memory. Don't be confused. So both of them have the pages, number of pages, because we divide by the same data structure that is called the pages. So this one is called the page 1, 0, 1, 2, 3, and so on. On logical memory. Logical memory means your program. Because from CPU, it doesn't matter whether this is in your hard disk drive, this is in the memory. So as long as the CPU can access the instruction, it's the same instruction on the memory and here. So this is called the logical memory. Then our goal is to allocate the page of the logical memory to the physical memory, which is called the page frame. So 0, 1, 2, 3. Then we need to have the same thing, mapping, whether this logical memory page 0 is allocated to for example, the 3. So this one goes 3, then this is a 3. Then the 1 is allocated to the 0, for example, and 0, and so on. Okay, some of them are free. For example, this is a free and free and free. Next time, if we execute another program and then find the free frame. So this is called the free frames. Same idea as the free blocks in your portable file system implementation. So operating system need to manage the free frame. Then whenever you find the need to allocate execute the program, which means logical memory, so you can find the free frames from the free frame list. Then allocate and update your page mapping table. Okay, so this is called the paging approach, paging allocation. Then how we can find, for example, CPU would like to access the program counter is for example the 20. Okay, so program counter is 20, so you need to check the pages. Pages, then the paging table, and find the physical location of this one, then finally access the data. This is the same process as we used in the contiguous and the segmentation approach. Benefit?
Less seats.
Maximize the utilization, which means no fragmentation issue, especially the external fragmentation, because we already divide the same size for the physical memory page frame. So if we have the leftover like this one, this will be external fragmentation, but usually not, because when the manufacturer designed this, mostly it's a 2 to the power. So usually we do not have such a remainder, so almost no the external fragmentation. Sometimes, maybe. So in case we use the multiple size of the pages, Sun Solaris system use the different size of the pages, maybe, but mostly it doesn't cause such an external fragmentation. What about the internal fragmentation? It's a little bit higher than the previous one. Why? Because, for example, this is the last one, but it needs only the 10 bytes. But due to the characteristic of the page, entire page should be allocated. Even though you need one, it's the same as the file allocation. When you allocate the file, the last block may has the 1 byte or 2 byte, and the other file, the free space you cannot use. So this is called the internal fragmentation. So for the internal fragmentation, maybe. So higher than the previous one, but it's comparing to the external fragmentation, it's much less, the impact. So this is the paging approach. So there are several things you need to consider if you implement the paging-based allocation. So think about if you develop the operating system, then the main part of the operating system is to create the process. Creating process, we need to create the system library, fork and exec. Then, if you are asked to implement the fork and exec system library, how can you do that? You need to decide, so do such a thing. Okay, how to using first you need to have the system library to use the memory allocation, then the memory allocation. So from the memory, so copy this one. How to copy? How to allocate? Page by page allocation. Then there are several issues you can realize this approach. So first one is we need to manage where's the free frames. Okay, we need to first know how many free frames. Okay, if you have like the 1 megabyte memory, yes, there was long time ago. The memory size is so small, so it's not a big deal to check all the page frame. But nowadays, what's the size of your memory? It's 8 gigabyte, 16 gigabyte each. The 16 gigabyte easily. Then, what about by the way, this size? Before that, page size. Bigger is the better. Smaller is the better? So
It's gonna be the
it's
same.
it depends on the the characteristics of the system. Okay. So usually if the page size is big, that is better for what? The batch processing. Or you can reduce the I/O. Okay, if you use the big size of the page. The problem, it may cause a lot of internal fragmentation. Okay, then, but if you have the small size of the page, it may cause a lot of I/O. You need to check all the time that this page, the table, mapping table. Okay, yes.
Professor, so for compared to a normal computer workstation, in this case, in this case, a supercomputer like
Yeah.
IBM Watson, they will have a completely different page size, will be much larger.
What do you think? The IBM Watson used a different? No, IBM Watson used the same AIX, the Unix system. Okay, they do not. But depending on your operating system, so they don't. You are not sure. That's the reason that I briefly mentioned. That you can have the multiple page size. Okay. So Solaris actually, I use the Solaris that support the two different size of the page. One is a 512 byte is most popular one, but not only just 512 byte, the 2K size. So depending on the characteristic of the program, the operating system allocate the bigger size the page, or sometimes the smaller size. But as far as I know, for example, IBM Watson was supercomputer. Each node and each computer is nothing but the one computer, just like the yours. Okay, it's not much different. And they are using the same version of the operating system, but that supported nowadays most of the supercomputer is not centralized. It's a distributed cluster system. Cluster means you have a number of nodes. Okay, by combining such a number of nodes, you can have the big power. That's called the supercomputer. But it was before maybe 10, 20 years ago, the supercomputer means it's a centralized bit. So you can possess the most powerful CPU and as big as possible for the memory size, then you can get the higher performance. But nowadays it's a cluster. Then the main problem of such a supercomputer based on the clustering is how to design such a number of nodes. It's a design, network congestion, and so on. And also how to reduce the overhead to access the memory that is updated by the other, and so on. Okay, so this is the pages. So there are several things. The one is the frame, so you need to consider, and the proper size of the page is another one. Okay. Then what if we have a number of program, number of the so I'm running the A program, B program, C program, but definitely such a total amount of size of the logical memory, which is the program, is much bigger than this physical memory. Then how can we address such a thing? So we will talk about how to address the issues that can be raised from this one. Okay. So mostly the proper size of mostly used size of the page is 512 bytes. Some of them is, I never seen such a big size of the page, the operating system, but mostly it's 512 bytes. But it is true, it's a power of 2, right? It makes sense. Okay. So this is a page. So when I'm talking about the page frame means this one, physical memory. On the other hand, when I'm saying the logical memory, sometimes a program, sometimes job, sometimes the process, sometimes logical memory. Logical memory means it's your program, your process, okay? Actually not process, program. So our goal is to map the program, logical memory to the physical memory, or the page frame. So, okay, that is our job. So this is a schematic, the view of how to use a page. So you can see the logical memory left hand side. What is this? Your program. So our goal is to allocate the page by page to the physical memory. How many page frame? How many? 8 of them. So for example, if each page size is the 512 byte, what is the size of your memory, physical memory? Page size is 512 byte. You have 8 of them. So 4K. So 4K is your physical memory size. And what about the program size? Actually, it's less than 2K. We are not sure how much bit, but let's say that if all of them is your program size is 2K at this time. Our goal is to map each logical memory page to the page frame number. So for example, page 0 is here, and the page frame number 1. Page 1 is the page frame number 4, which means so we need to manage the page table, mapping table. It's the same as a segmentation mapping table and MMU, the table that we have seen in the contiguous location, same thing. So left-hand side is the logical memory page number, right-hand side is a physical page frame number. So this will be the managed. Where is it? It's also in the memory, which means we need to have another register, okay, to know where is the starting address of this paging table and the limit, the length of this paging table. Then finally we can access this one. Okay, so then our address. So for example, from the CPU to access the specific instruction. If so far we talk about the addressing as just the address of the memory, then the CPU can access the data. However, from now on, we are going to use what? Page. So our addressing format should be changed by considering the page number. Then instead of if we are using the contiguous allocation, especially the single, the contiguous allocation, like the MS-DOS, we can use the addressing binding during the compiling time and fix the address. So using the address of the physical memory, we can find the location. However, from now on, because we are using the page, so some part of our address should represent the page number. Then the other part doesn't have to be entire. So for example, this is let's say page size is here 4 byte, too small, 8 byte. Okay, so this is 8 byte, 0, 1, 2, 3, and 7, and this one is also 8 byte, 8 through the 15 and 16 and something like that. Okay, then to represent the address location of the specific instruction. For example, suppose that this is in the 10. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is the program counter. We try to access this instruction. At that time, to represent this address, first the page number. Page number is 0, 1. So 1. Instead of 10, it's the offset. Offset means how far from the beginning. Okay? So 0, 1, 2.